So today we are going to see single phase fully controlled rectifier or single phase fully controlled converters. So fully controlled in the sense, so all the devices are fully controlled devices, that is we are using SCR for, it is a single phase full wave rectifier, for it is constructed using SCRs and it is fully controlled in the sense we can vary the output voltage. It is a half wave controlled rectifier means we can control only positive half cycle and we will get only the positive half cycle as output. So in fully controlled rectifier means we can vary the output voltage for both positive half cycle and negative half cycle. So that is called fully controlled. So for varying the output voltage we are using the controlled devices. So here we are using SCR, that is controlled device. And first thing we can see for the resistive load. So what is so we can understand what is the difference between controlled and uncontrolled rectifier means. Controlled rectifier in the sense we can vary or control the output voltage. Uncontrolled rectifier means you cannot vary the output voltage. So controlled rectifier is constructed using any of the controlled device, that is SCR, IGBT, MOSFET or any controlled device. An uncontrolled rectifier is constructed using uncontrolled device, that is only diode. And it is a fully controlled rectifier in the sense it is a full wave rectifier, so we can get output in both the positive half cycle and negative half cycle. So fully controlled rectifier means it is a full wave rectifier with controlled device as SCR. So this is the circuit diagram for the single phase full wave controlled rectifier, and we are having four thyristors T1, T2, T3 and T4, and input is an AC voltage source, that is Vs, that is equal to Vm sin omega t. So it is represented by, it's an expression Vm sin omega t, where Vm is the maximum value of the sinusoidal voltage and sin omega t is the nature of the waveform, and V0 is the output voltage and I0 is your output current. And we can study the operation of this rectifier, that is for each half cycle two devices will be conducting, that is two oppositely diagonally paired thyristors, that is for positive half cycle T1 and T2 will be conducting, and for negative half cycle T3 and T4 will be conducting. So for positive half cycle the current will flows in the direction, that is from Vs to T1, then next to resistance and to T2 and to the negative or neutral terminal of the supply voltage source. That is for positive half cycle T1 and T2 will be forward biased and it will start the conduction after the giving input gate pulses. So the firing angle or the gate pulses are applied at an angle of delay angle or firing angle alpha. From the alpha it will start the conduction and it will conduct up to the end of the positive half cycle, that is pi. So in normal uncontrolled rectifiers, when we are using diode means the for positive half cycle it will conduct for 0 to pi, and here it is conducting for alpha to pi. So by varying the alpha from the instant of 0 to maximum of 180 degree, that is pi, we can vary the area of the positive half cycle, so that it is indirectly varying the magnitude of the average output voltage. That is, this is a controlling, that is phase controlled converters. So this is called phase controlled converters. So phase controlled converters in the sense by varying the phase angle, that is alpha, we are varying the output voltage or we are controlling the output voltage. So that it is called as phase controlled converters. So it is alpha plays an important role, that is firing angle. So by varying alpha from 0 to 180 degrees, we can vary the output voltage from maximum value to 0 voltage. So for alpha is equal to 0 degrees, we will get the maximum output voltage, and for alpha is equal to pi, that is 180 degree, we will get 0 output voltage. So for positive half cycle T1 and T2 will be conducting at from the angle alpha. So this is the firing angle alpha. So first waveform is a source voltage waveform. So source voltage waveform which is shown in solid line represents the actual waveform and the dotted line represents the inverse of that waveform. So we can say VAB and its inverse is VBA. So since it is a full wave rectifier, in both the half cycles, the devices will be conducting so that the inverse of the voltage is drawn. and second and third will be the gate pulses for the for each half cycle conducting thyristors. Ig1 and Ig2 are the positive half cycle conducting thyristors, and Ig3 and Ig4 are the gate pulses for the negative half cycle conducting thyristors T3 and T4. So first one, then third will be the output voltage V0. So V0 is the output voltage waveform, and we can get 0 to alpha or 0 to pi. T1 and T2 will be in forward bias, but it will start the conduction at the alpha after giving the firing pulses. So from 0 to alpha there will not be any conduction, so no devices will be conducting, so the output voltage will be 0. And from alpha to pi, T1 and T2 will be conducting, and the output voltage will follow your input sinusoidal voltage waveform. And next one, for negative half cycle, it starts from pi to 2 pi, and we are giving the firing pulses for the negative half cycle conducting thyristors T3 and T4 at an angle pi plus alpha, so that it starts the conduction from pi plus alpha and it finishes it at 2 pi. And so since we are giving firing pulses at pi plus alpha, pi to pi plus alpha, there will not be any voltage. V naught equal to 0. From pi plus alpha to 2 pi, it will follow the input voltage, that is sinusoidal waveform. So we can directly derive the that is nature of the waveform from the sinusoidal input voltage. So that I have drawn the inverse of the voltage. And pi plus alpha to 2 pi, this will be the negative of cycle conduction by the thyristors T3 and T4. And next one, 2 pi to 2 pi plus alpha, again 0. And 2 pi plus alpha to 3 pi, again T1 and T2 will be conducting. So since it is a positive half cycle, and for the next second negative half cycle, T3 and T4 will be conducting from 3 pi plus alpha to 4 pi. And since it is a resistive load, the voltage, output voltage and output current V0 and I0 are in phase. So both the voltages and current waveforms will be of similar in nature. Both the waveforms are looking like similar waveforms, but the magnitude alone will differs. Already we have seen in the lab. So V0 will have the maximum of, if we are giving 230 volt as input voltage means, so the 230 volt will be the RMS voltage. So root 2 into Vrms, root 2 into 230 will be 325 volts. So that will be the maximum voltage. So if we are giving 230 volt means the output voltage maximum of will get us 325 volts. And the current, if we are using a resistance as 10 ohms means the voltage divided by the resistance will give the maximum magnitude of the I0. That is, if we are using 325 volt maximum voltage and resistance as 10 ohms means we will get the I0 value of maximum current as 32.5 amps. So this is the V0 and I0 output voltage and output current waveform. Simply it is, you can draw the waveform by using a sinusoidal waveform. So but there will be a distortion, or but there will be a zero period at the 0 to alpha and pi to pi plus alpha. But the instant after the giving the firing pulses, it will start the conduction, that is from alpha to pi and pi plus alpha to 2 pi. It will follow the sinusoidal nature, and the remaining periods are the zero voltage periods. So 0 to alpha, pi to pi plus alpha are the zero voltage periods, and the remaining periods are the sinusoidal voltage periods. It will follow your nature of the input voltage, that is sinusoidal voltage. And the next one, VT1 and VT2 are the voltage across the thyristors or voltage across the SCRs. So whenever the SCRs are conducting, the voltage across them is 0, and whenever the thyristors are not conducting, it will be in off position. At that condition, the input voltage is applied as across that devices. So we can draw the voltage across thyristor waveform as first one, 0 to alpha, VT1 and VT2, that is thyristor 1 voltage and thyristor 2 across voltage are same as that of your input voltage. So that will be a it will follows the sinusoidal input voltage waveform, since both the devices are in off condition. Since we are not giving the firing pulses, we are giving only at the alpha, so it will turn on at alpha and it will conduct up to pi. So up to that it will be 0 to alpha, it will be in off condition. So the full voltage is applied across the thyristors. So 0 to alpha, the full input voltage is across the thyristors. So we will get the same as that of the input voltage, and alpha to pi it will conduct. T1 and T2 will be conducting, so VT1 and VT2 are 0. Or in practical cases we will have some minimum voltage, that is on-state voltage drop across the device. Then next one, pi to 2 pi, also the T1 and T2 are in reverse bias condition, so that the negative off cycle voltage is applied across the resistors T1 and T2. So we will get the output, that is VT1 and VT2 as like this. And VT3 and VT4. VT3 and VT4 conducts only for the negative half cycle. So that is pi plus alpha to 2 pi. At that condition only it will have the zero voltage, that is conduction period, and remaining periods it will follow the input voltage waveform, that is 0 to pi reverse bias. So it will the positive voltage of the positive half cycle of the input is applied as reverse voltage or reverse bias voltage for the resistors T3 and T4, so that it is marked as negative half cycle in VT3 and VT4. And pi to pi plus alpha also it will be in forward bias condition, but it will not conduct since the firing pulses are not given. So pi to pi plus alpha we will get the positive spikes like a voltage, and pi plus alpha to 2 pi it will be conducting, so the voltage across them is 0. And again 2 pi plus 2 to 3 pi, again it is reverse bias, so we will get the voltage input voltage as reverse voltage across the T3 and T4. So this is the voltage and current waveforms. So these are the waveforms we have to study, that is output voltage, output current, and voltage across the resistors we have to clearly draw for any angle, firing angle. So alpha can be varied from 0 to pi. When alpha is equal to 0 degrees, you will get the full output voltage waveform. When alpha is equal to 90 degree, you will get the half the portion of the positive half cycle, and alpha is equal to 120 degree, you will still the area of the curve is reduced. So all the waveforms are plotted against the magnitude to omega t. Omega t is in radians, that is omega is equal to 2 pi f and d is equal to time period. So it is a omega t is in radians, and we can draw it in degrees. So these are the explanations. The circuit consists of 4 thyristors T1, T2, T3 and T4, and a voltage source Vs and a R load. During the positive half cycle of the input voltage, the thyristors T1 and T2 is forward bias, but it is not conducting until a gate signal is applied to it. When a gate pulse is given to the thyristors T1 and T2 at omega t is equal to alpha, it gets turned on and begins to conduct. When T1 and T2 is in on condition, the input voltage is applied to the load through the path Vs, T1, load, T2 and Vs. During negative half cycle, T3 and T4 are forward biased. The thyristor T1 and T2 gets reverse biased and turns off. When a gate pulse is given to the thyristor T3 and T4 at omega t is equal to pi plus alpha, it gets turned on and begins to conduct. When T3 and T4 is on, the input voltage is applied to the load Vs through this path Vs, T3, load, T4 and Vs. Hence, here the load receives the voltage during both the half cycles, positive and negative half cycle. The average value of output voltage can be varied by varying the firing angle alpha. So already we have shown the plot of input voltage, gate current, output voltage, output current and voltage across the thyristors. So next we can derive simple derivations for the average output voltage. In all the cases we will derive the average output voltage, RMS output voltage, average output current and RMS output current. So first thing we can derive the average output voltage. So V naught is equal to, that is here from this diagram, V naught is equal to VDC, that is equal to, how we can derive means, that is area under the curve divided by the time period. So we can area under the curve means, so for the output voltage, the area under the curve, that is we can derive for 0 to 2 pi, and it is a half wave symmetrical waveform. Half wave symmetrical waveform means from 0 to pi we will have some waveform. The same will be replicated, and the same will be appearing in the output. The same voltage waveform nature will be followed in pi to 2 pi. So the positive and negative half cycle are the period from 0 to pi, and pi to 2 pi are symmetrical, both are same. We can derive only for 0 to pi, or we can derive for 0 to 2 pi means, so we will get the same output expression. So directly we can derive for 0 to pi as time period. So the formula is area under the curve divided by the time base. So the time base can be 0 to 2 pi, that is 2 pi is the time base, and for area under the curve means 2 times, that is 2 times we are getting the positive, that is positive half cycle. So here we are directly deriving it for a single half cycle, since the output voltage waveform is symmetrical. The time base is pi and V naught is we are getting from 0 to pi for normal cases, and we can omega t, the firing angle can be varied from alpha, that is alpha is equal to 0 to pi. So we can substitute, instead of 0 we can substitute this alpha, and 1 by pi into alpha to pi. V naught is nothing but it is following your input voltage waveform Vm sin omega t. That is Vm is the maximum voltage, sin omega t is the nature of the waveform, and we are integrating with respect to d omega t. So Vm is a constant term, we can take it outside, and we are integrating sin omega t with respect to omega t. On integrating that, we will get minus cos omega t, and after that the limits are alpha to pi. So we have to substitute the limits, that is minus cos omega t. This upper limit is pi and the lower limit is alpha. So minus cos pi, minus of minus plus cos alpha, and cos pi is equal to minus 1. So minus into minus plus, that is 1 plus cos alpha. So that we will get the V naught, the output average output voltage expression as Vm by pi 1 plus cos alpha. And next thing, we can derive the RMS output voltage. So here also we can have the time base as 2 pi, or simply we can derive for one cycle pi. So if we are deriving it for 2 pi means we have to time base we have to take the time base as 2 pi, and in the numerator we will have the 2 for 2 times the half cycles. So for 2 half cycles we will multiply it by 2, so both the 2 get cancelled, so we will get the 1 by pi. And for RMS, calculating RMS output voltage, the limit should be the same, that is alpha to pi, and it should be squared and it should be taken square root. So that is the RMS, root means square value. So the Vm sin omega t has to be taken square, that is Vm square sin square omega t, and after that we will have to take the square root, that is to the power of 4 to the power of 1 by 2. So here sin square omega t can be written as, so for integrating the sin square omega t we have to write the sin square omega t is equal to 1 minus cos 2 omega t. So this expression becomes the second expression, that is Vm square, it is a constant term, so we can take it outside, and the next thing will be the 2 pi divided, so the 2 will not be there, so 2 gets cancelled, Vm square by, sorry, 1 minus cos 2 omega t by 2, so Vm square, we have taken it outside, and 1 minus cos 2 omega t by 2, the 2 is also a constant, we can take it outside, and already pi is there, so the constant term is Vm square by 2 pi, and we have to integrate the 1 minus cos 2 omega t with respect to omega t. So if we are integrating means, so the Vm square by 2 pi, we can take it outside from the square root, that is Vm square to the root of Vm square is Vm, and 2 is taken outside, so it can be root 2, and 1 by pi is it is inside, and we are integrating 1, that is constant term, so it will be d omega t, 1 into d omega t to the limit of alpha to pi minus cos 2 omega t to the limit of alpha to pi with respect to d omega t. So it is 2 times there, it will not be like this, and after that, on integrating 1 we will get simply the omega t for a limit of alpha to pi. On integrating cos 2 omega t we will get sin 2 omega t by 2. So these things you can refer in any maths book, the integration and differentiations. So for integrating 1 we will get the answer as omega t, and for integrating cos 2 omega t we will get sin 2 omega t by 2 to the limit of alpha to pi. After substituting the limits, that is upper limit and lower limit, so upper limit minus lower limit, that is pi minus alpha for omega t, and sin 2 omega t, so sin 2 pi by 2, sin 2 pi minus sin 2 alpha by 2, and to the power of whole power 1 by 2. So all the sin pi terms are sin 2 pi 3 pi, all sin pi terms are 0, so that we can neglect that sin 2 pi terms, and after that we will get pi minus alpha plus sin 2 alpha by 2. So this thing we will get as output voltage, output RMS voltage, that is RMS value, that Vm by root 2 into 1 by pi, pi minus alpha plus sin 2 alpha by 2 to the power of 1 by 2. Then average load current will be I0 DC, that is IL average, that is equal to V0 DC by RL. The same thing we have derived over here, Vm by pi 1 plus cos alpha divided by R. So the output RMS, output average current will be Vm by pi R into 1 plus cos alpha. And similarly, we can derive the RMS output current, that is V0 RMS divided by RL. So this thing, the whole term Vm by root 2 into 1 by pi, pi minus alpha plus sin 2 alpha by 2 to the power of 1 by 2 divided by R will give the RMS output current. So average output current and average load current and average output current will be same. So average output voltage divided by resistance will give the average load current, and RMS voltage divided by resistance will give the RMS output current. And next we will see the control characteristics. So control characteristics in the sense of how much we are controlling, what is the range, or what is the range between in between the output voltage is controlled, so that we can plot or that we can study in the control characteristics. So already we have derived, it is calculated from the average output voltage. Since it is a DC voltage, the average output voltage plays an important role. So from the average voltage expression, there is Vm by pi 1 plus cos alpha. So here the alpha can be varied from 0 to 180 degrees. So when alpha is equal to 0, we will get some VDC, and when alpha is equal to 180 degree, we will get some VDC. So when alpha is equal to 0, so cos 0 is equal to 1, and 1 plus 1 to Vm by pi. That is maximum DC voltage that can be obtained is when alpha is equal to 0. When alpha equal to, substituting for alpha equal to 0, we will get the VDC maximum value as 2 Vm by pi. So this is the maximum value for the single phase fully controlled rectifier. Similarly, we can substitute alpha is equal to 180 degrees. So cos 180 degree is minus 1. So 1 minus 1, 0. So VDC is equal to 0. When alpha is equal to 180 degree, the output voltage is 0. So by varying alpha from 0 to 180 degrees, we can vary it from the maximum voltage of 2 Vm by pi to 0. So this is we are plotted over here. For alpha is equal to 0 degrees, we will get the VDC max, that is our maximum output voltage is 2 Vm by pi. So 2 pi pi is, will be the 0.636619 Vm, and for alpha is equal to 30 degree, we will get 0.59 Vm, and for alpha is equal to 60 degrees, we will get 0.47 Vm, and for alpha is equal to 90 degrees we will get 0.318 Vm, for 120 degree 0.19 Vm, 150 degrees 0.042 Vm, and 180 degree it will be 0. So we can see for every increase in angle alpha, we will see the decrease in output voltage. First thing, 63% of Vm for alpha is equal to 0 degrees, and for 90 degrees it will be off, that is 0.31%, and for 180 degrees it will be 0%. So this thing we can plot by making the x-axis as alpha and y-axis as a V0, that is average output voltage. We will get a sinusoidal nature of control characteristics. For alpha is equal to 0 degree, we will get the VDM, maximum voltage of 2 Vm by pi, and for 60 degrees, we'll have some magnitude of 47% of Vm, and for 120 degrees we will get as 19% of Vm, and 120 degrees it will be 0. So this is the control characteristics. So from that we can see for alpha is equal to 0, we'll have maximum voltage, and alpha is equal to 180 degree, we will get the 0 voltage. Thank you.